Hello again. So this is Anti-Relativity Lesson 2. Relativity is a mess. There are lessons in special relativity. The aim here is to try to counteract that and give lessons in anti-relativity. And the way to do that is to point out what is being taught in relativity lessons is nonsense. Over the years, the teaching of special relativity has been to pile on more nonsense. So I'm going to contrast how the teaching has changed. Taking as example what was said in the 1982 book on relativity and what was later said in 1991 when the book was updated. So what I'm doing is I'm comparing these two books, Introduction to Special Relativity by Wolfgang Windler, and he published it in 1982 and then he updated it with the second edition in 1991. So I'm going with the second edition of the book and pointing out when different to the first edition. The aim is to show that the methodology of teaching relativity is to move the goalposts. Some nonsense is said, but that is never enough, and some extra nonsense then gets added later. Moving goalposts is making changes. It's supposed to be a fallacy, but believers in relativity seem to treat it as a virtue to do that. So diving straight into chapter 1, section 3. In addition to, it says the following: inertial frames and special relativity. A frame of reference is a conventional standard of rest relative to which measurements can be made and experiments described. For example, if we choose a frame rigidly attached to the Earth, the various points of the Earth remain at rest in this frame while the fixed stars all trace out vast circles in the course of each day. And actually, when we talk about fixed stars, that's approximately fixed, I think. If on the other hand we choose a rigid frame attached to fixed stars, then these remain at rest while points on the Earth other than those on its axis trace out approximate circles in the course of each day, and the Earth itself traces out an ellipse in the course of each year, and so on. Among all possible reference frames, there is one class which plays a special role in classical mechanics, namely the class of inertial frames. So this is a photograph. Long exposure shows you what happens in the sky. The stars sort of move around relative to us. Edition 2 carries on. These frames play an even more fundamental role in the special theory of relativity, and we shall therefore define and discuss them carefully. An inertial frame is one in which spatial relations as determined by rigid scales at rest in the frame are Euclidean, and in which there exists a universal time in terms of which free particles remain at rest or continue to move with constant speed along straight lines, i.e. in terms of which free particles obey Newton's first law. And so that is extremely confusing, so I will bring in a sentence earlier to that. So earlier it was saying all possible reference frames, there is one class which plays a special role in classical mechanics, namely the class of inertial frames. So he's talking of classical mechanics. Next the text says these frames play an even more fundamental role in the special theory of relativity, and we shall therefore define and discuss them carefully. So now he's talking about special relativity. He was talking about classical mechanics one moment, and the next moment special relativity. So are they supposed to be the same thing? Question mark. So it's another area, another one of those areas that relativists like to confuse things. Sometimes classical physics is used to be Newtonian physics, and sometimes classical physics is used to mean both Newtonian physics and Einstein's relativity, because sometimes it's thought of in terms both Newtonian physics and Einstein's relativity are not quantum physics, and any physics not quantum physics is called classical physics, and in other times it's thought Newtonian physics is classical physics and not Einstein's relativity, i.e. terms are muddled up, and that's indicating of how they mess things up. So the book's after saying these frames play an even more fundamental role in the special theory of relativity, and we shall therefore define and discuss them carefully. He's talking about special relativity, and then he goes on to mention Newton. And he says an inertial frame is one in which spatial relations as determined by rigid scales at rest in the frame are Euclidean, and in which there exists a universal time in terms of which free particles remain at rest or continue to move with constant speed along straight lines, or in terms of which free particles obey Newton's first law. Thus, what he's doing, he's talking about inertial frame in context in Newtonian physics, and not saying how connected to inertial frame in special relativity context. He's glossing things over. So we've got three-dimensional space is Euclidean with a universal time, and that's Newtonian. With Einstein, he goes for four-dimensional space-time. The book, the second edition, continues. Free particles are placed without velocity at fixed points in an inertial frame will remain at those points by definition. And what he means probably is by definition of inertial frame, but he's not making it clear what definition he's really talking about. Anyway, he continues, we can therefore picture an inertial frame as an aggregate of actual or virtual free test particles mutually at rest as determined by rigid scales. The distance between these defining particles satisfy the Euclidean axioms, an important stipulation in view of later development. Straight lines in such a frame can be defined as G6, and that's lines of minimum length, and free particles not belonging to the defining aggregate move along such lines. We can further picture the defining particles as carrying clocks that indicate the universal time throughout the frame. And the book, he doesn't say what the Euclidean axioms are, but I'm going to pass on that. Particles carrying clocks with the universal time would be an idealized thought experiment. The thing is with these relativity texts, they're giving ambiguity. A naive reader student expects them to clarify things later, but often they don't. At the moment, the text has ambiguity over how to deal with inertial frames in Newtonian context versus in the special relativity context. The hope is that it will eventually be clarified, but it doesn't. So edition 2 says we shall consider two inertial frames equal if they have the same defining particles. The choice of coordinates within such a frame is still free once it is made. One should logically use a different term for the frame plus its coordinates, such as inertial coordinate system. In practice, however, we shall usually be less precise and let the context define which of the above we mean by inertial frame. So I note that this paragraph is not in edition 1, he's added it in edition 2, and what we have is inertial frame can be used to mean at least two different things. Its vagueness of terminology is a feature of special relativity. In edition 1 and 2 he says, now let us see the relevance of all this to special relativity. We shall adopt the modern view, largely due to Einstein, that a physical theory is an abstract mathematical model, much like Euclidean geometry, whose application to the real world consists of correspondences between a subset of it and a subset of the real world. This means that physics just becomes mathematics, and how to interpret physical reality through that mathematics. Several disciplines disagree with doing that, but as for myself, I go along with this idea. Edition 2 carries on. In line with this view, special relativity is the theory of an ideal physics referred to an ideal set of infinitely extended gravity-free inertial frames, such as we described above, and he's given a footnote with that, and this footnote is in edition 2 but not in edition 1. So reading that footnote, on a more sophisticated level, the arena of special relativity will eventually, that's in chapter 4, be seen to be Minkowski's four-dimensional spacetime. This is an abstraction from the set of all inertial frames. At first, however, we shall rely on the set of inertial frames itself to formulate the theory. And so he's pointing out the abstraction that it's becoming. He picks up the issue of gravity-free when he says, why gravity-free? Classically, gravity was regarded as an overlay which did not affect the rest of physics. So it was logical for Newton to treat the frame of the fixed stars as inertial, in the sense that but for gravity-free particles would move uniformly relative to it. Now it seems odd to have inertial frames not able to deal with gravity, and the excuses for this are contrived. Continues, but Einstein, in his general relativity, the details of which are beyond the scope of this book, and so it's a thing to note, he's hiding things you can't deal with, particularly in special relativity, is supposed to be dealt with at a later stage. Taught as that gravity is curvature of space and time, and so affects all the rest of physics, which has no choice but to play on a stage of space and time. Particles not subject to forces except gravity move as straight as possible in curved space-time. So he's bluffing it all off for this as being beyond what is being taught in a special relativity text. And that's another standard trick, just bluff things off to supposed to be dealt with at a later stage. So what we have now is a footnote from edition 1 that is not in edition 2, and it says in that footnote actually the rate of change of gravity, and it refers to what is being said when he says that gravity is curvature of space and time, and so affects all the rest of physics. So it's difficult to understand what is meant by rate of change of gravity, and by saying gravity is curvature of space and time. If thinking of gravity as acceleration could be meaning acceleration is curvature of space and time, ? It's not very clear. I don't know how any relativists would agree with that claim, and it's presumably why it was removed. So this is the usual vagueness in discussion things in relativity. It's just unclear lots of the time. So there's a lot of arguing over whether inertial frames can deal with gravity, but what is to note is the text does not want to go into details about that, and so in order to move on with the text I pass on this issue. Edition 2 has the following. In Whittaker's phrase, gravity ceased to be one of the players and became part of the stage. So the text is going by is this book by Whittaker. So to get a rough view of that book, let's look at Wikipedia. Wikipedia talks about it. It says the book, A History of the Theories of Ether and Electricity, is any of 3 books written by British mathematician Sir Edmund Taylor Whittaker on the history of electromagnetic theory, covering the development of classical electromagnetism, optics and ether theories. Several parts of that book are controversial, as Wikipedia notes. Chapter 2 of the book is highly controversial, it says, this is Wikipedia, and constitutes Whittaker's major role in the relativity priority dispute. Whittaker's view on the history of special relativity is that Lorentz and Poincaré had successfully developed the theory before Einstein, and the priority belonged to them. Despite Whittaker's objection, scientific consensus remains strongly in favour of Einstein's priority on the theory, with authors noting that while the theories of Poincaré and Lorentz are mathematically and experimentally equivalent to Einstein's theory, they are not based on the relativistic postulates and do not constitute what is now known as Einstein's relativity. While parts of the book have received notable praise due to the role in the historical controversy, the book overall has been said to fall short of the standards of the others, and it has historically received many fewer citations. So back to me, in Whittaker's view, special relativity came from Lorentz and Poincaré and not starting with Einstein, a view that others have disagreement with. The relativity text by Rindler is not going into that issue, so Rindler is going by a source that not all relativists agree with. As many distants like to point out, Lorentz's theory is a different theory to Einstein's theory, so Rindler is not going into details of Lorentz's theory versus Einstein 1905 theory as to whether they are the same theory or different theories, etc. So he's just glossing over relativist confusion. Ideally, Rindler teaching Einstein's relativity, not Lorentz theory, or maybe he's teaching Lorentz theory after all, ? And using Whittaker as information source should say why he agrees or disagrees with the Poincaré-Lorentz versus Einstein issue, but of course he doesn't, instead just glosses over and leaves the confusion. So back to what the book is saying. Thus, extended inertial frames cannot be realized in nature because gravity destroys equidisty. And that word, I don't know what it's supposed to mean, but presumably what he means is it destroys Euclidean geometry. He continues, the book continues, but this does not affect in any way the logic of special relativity as an abstract theory, just as it does not invalidate Euclidean geometry. So it destroys Euclidean geometry but does not invalidate Euclidean geometry, which really means is not go by the same assumptions as Euclidean geometry. But what those assumptions are is not going to be actively dealt with by the book. And the book continues, it does however put limitations on its correspondence with the real world. These are spelled out by Einstein's equivalence principle of 1907, on which he eventually based his general theory of relativity. The reference frames in the real world that correspond to that portion of the ideal inertial frames discussed in special relativity are the freely falling, non-rotating local frames. At any given place and time in the real world, there is a family of such frames, each member of which can be realized by an aggregate of test particles momentarily at rest relative to each other and falling freely under gravity. So what he's doing is not adequately dealing with, because general relativity is not what the text is dealing with, as pointed out earlier in the text. He's dealing with special relativity, not general relativity, so it's more bluffing off. So Rindler continues, certainly in Newton's theory such a local frame is equivalent to an inertial frame from which gravity has been eliminated, for in a gravitational field all particles suffer the same acceleration. Most of us have at least voraciously experienced such freely falling local frames. We need only recall the televised pictures of space capsules in which astronauts are weightless and, if unrestrained, move according to Newton's first law. Such capsules, evidently of limited extent, are the primary reference frames in the real world, relative to which the laws of special relativistic physics would be expected to apply most accurately. So what he's doing now, he brings in the term local frame, presumably meaning a frame that experiences gravity, but gravity is so small that you can approximately treat it as an inertial frame, where the inertial frame has no gravity, but really he's not explaining things very well. Edition 2 gives a footnote. There is a close analogy between plane Euclidean geometry and its application to small portions of curved surfaces, like the surface of the Earth on the one hand, and special relativity and its application to small portions of the real world curved by gravity on the other hand. And that footnote is not in edition 1. When it says real world, I should really be saying something like real universe, or else confusing with the Earth being curved when meaning space-time being curved. So Rindler carries on and he says, in this book all reference frames used, unless otherwise stated, will be ideal, infinitely extended, gravity-free inertial frames, and all observers will be considered to use such frames, inertial observers. Sometimes the term inertial may be omitted, but it will always be understood. So what he's doing basically is talking to something about idealized situation. The book continues, it will turn out that just as in Newtonian mechanics, the ideal inertial frames of special relativity are all in uniform translatory motion relative to each other, and conversely that any frame having such motion relative to an inertial frame is itself inertial. It will also turn out as a direct consequence of the relativity principle that all inertial frames are spatially homogeneous and isotropic, not only in their assumed Euclidean geometry, but for the performance of all physical experiments. By this we mean that the outcome of an experiment is the same whenever its initial conditions differ only by translation, homogeneity, and rotation, isotropy, in some inertial frame. So what he's doing is been talking about an idealized situation, and now he's bringing in the relativity principle. So does it mean relativity principle only applies to an idealized situation? Text omits to say, thus leaving it ambiguous. In my view, relativity principle only applies to some idealized situation and does not apply to actual physical situations, because really treating most all frames that experiences some sort of acceleration, therefore not the idealized inertial frame to which the relativity principle applies. As an idealized Serena situation could treat one frame as an inertial frame as having never experienced acceleration, but all other frames as having experienced the acceleration, and thus not be an inertial frames. And the one frame being treated as inertial would be the preferred frame, i.e. in such a situation the relativity principle is not applicable, because relativity principle ideally says no preferred frame, but suddenly gone against the principle and made it a preferred frame. The book carries on. It may be noted that whereas our definition of inertial frame already determines the rate of time in each inertial frame up to an overall constant factor as that in which free particles move uniformly, isotropy determines the clock 0 point setting up to an overall additive constant. For suppose isotropy holds an inertial frame referred to Cartesian coordinates x, y, z, and we determine a new time t prime is equal to t plus kx, where k is a constant greater than 0, then Newton's first law will still hold, but any given rifle will now shoot bullets faster in the negative x direction than the positive x direction, i.e. greater coordinate velocity. The text has not actually introduced the relevant maths of Lorentz transformation so far, so it's jumping ahead of itself. So what he's just said is confusing. So addition 2 says the following: again, as a consequence of the relativity principle, it will presently turn out that inertial frames are temporally homogeneous, i.e. that identical experiments relative to a given inertial frame performed at different times yield identical results. In particular, this implies that all methods of timekeeping based on repetitive processes are equivalent, and it denies such possibilities envisaged by E.A. Mill as that inertial time relative to which free particles move uniformly falls out a step over the centuries with atomic time, e.g. that indicated by a cesium clock. And addition 1 instead of that says the following: as a final axiom, we assume that inertial frames are temporally homogeneous, i.e. that identical experiments relative to an inertial frame performed at different times yield identical results. In particular, this implies that all methods of timekeeping based on repetitive processes are equivalent, and it denies such possibilities envisaged by E.A. Mill as that a inertial time relative to which free particles move uniformly falls out of step over the centuries with atomic time, e.g. that indicated by a cesium clock. So now to go through these differences between the two different editions. Going by what edition 2 says, again as a consequence of the relativity principle, it will presently turn out that inertial frames are temporary homogeneous, while edition 1 says, as a final axiom, we assume that inertial frames are temporary homogeneous. So it's big changes on that issue. Edition 1 makes it sound like an extra assumption, and edition 2 makes it a consequence of the relativity principle. The text is of course not going into sufficient detail. If consequence, then how is it not going to, how is that, he's not going to say, just the usual mess by relativists. What said next is same in both editions, namely, i.e. that identical experiments relative to inertial frame performed at different times yield identical results. Ambiguous because not saying how it's identical, as in the rest is ambiguous because not going into details about what E.A. Mill thinks. And it says, in particular, this implies that all methods of timekeeping based on repetitive processes equivalent, and it denies such possibility envisioned by E.A. Mill. Well, what were those? It doesn't going to tell you what those were. Conclusions. So what we can see is the text is making a total mess of things, and that mess is the sort of things taught to students. It takes a greater understanding of relativity than newbie to relativity has to realise that what is being taught is a mess. Thus the procedure is a person new to relativity gets taught it and then researches what he or she was taught and then realises relativity is a mess and then becomes a dissident. The mainstream then responds to such a person by calling them a crank or crackpot, even though that person has big understanding of relativity and knows relativity is a mess. Thank you, and that's the end. Finish this talk.